to conclude our discussion on timber, let us look into some additional issues on structure of timber. Then we shall see moisture effect, seasoning, properties, some important properties, and you see the timber today is in a large scale used as industrial products, as boards and particle boards, plywoods and so on. So, we will discuss more on them within our time limits, because additional discussion on actually timber as a product, as a structural timber as a product, that is not being covered in this lecture because of the paucity of the time. So, we will look into industrial products instead, because which are definitely more efficient use of the timber. So, let us continue with our discussion on molecular structure. We did not talk about, we just said that it has what type of growth of the tree we looked into, and we talked about sapwood, the heartwood, etc., and also we talked about conversion, but we did not talk about what the molecular structures of wood look like. Now, molecular structures of wood, if you look at it, it is actually cellulose or the fibers, right. Is the formula of cellulose is this, that constitutes about 40 to 50%, and the crystalline cellulose, actually it is crystalline, highly oriented 3D molecules, right, and its degree of polymerization or number of molecules in the chain could be 7,000 to about 10,000, the filament formation in form of filaments. So, this is the kind of fibers which are there in the wood. Then the other same one, hemicellulose, same formula, but that is semi-crystalline and 20 to 35%. So, 40 to 50% is this, 20 to 35% is this, and this obviously is much shorter chain length, 500 to 1000 is the degree of polymerization. So, these are the two fibrous materials, those are present in the wood, and the other group which is present is the lignin phenyl group, that forms by and large the matrix part of it, 15 to 35% amorphous and large 3D molecules, this is resistant to fungi. So, these three are the main chemical constituents of wood, and the other extractives are 2 to 10%. These are responsible for color, as you get in the wood, for example, teak wood has got its or for that matter, for example, mango wood, which is yellowish in color. So, there are different burnish colored wood, let us say, some woods are yellow color, some wood are reddish color. So, the extractives are responsible for the color of the wood, right. So, that is the chemical structure of the wood, but most important is the moisture in the wood. About 20 to 30% water in wet wood is chemically bound. You see this water, as we have discussed earlier also several times, that water can be bound chemically and physically, adsorbed water, then capillary water, etc., and mechanically held water and so on. The same thing goes on in case of wood as well. So, about 20 to 30% water in wood is chemically bound, and there is about there is some moisture content which is about 27%. So, I will say this is about 27% moisture content, around 27% moisture content, 27% moisture content, right, about 28% moisture content, 28% moisture content. Cavities of the wood cell remains filled. Now, this is chemically or physically bound, actually chemically bound, some amount of it is physically bound, and higher moisture content there fills the cavities of the wood cell, higher moisture content fills the cavities of the wood cell. So, when you dry the wet wood, the cell moisture is lost fast, which are capillary water in larger cell cavities which are there, which are not chemically or physically bound, mechanically held or capillary bound, they would be actually removed fast, right. And this does not result in any dimensional changes, because structure of the material has not changed If you remember, there is an analogy in case of concrete also. If you have capillary waters lost, there is no much dimensional changes, but when you have physically adsorbed water is removed, there can be dimensional changes. So, when cell cavities are empty, but cell cavities are empty, but cell walls retain their bound water, right, because the cell structure is such that it has got a cavity inside, then the boundaries have bound water, and this state is said to be fiber saturation point. This state is said to be fiber saturation point, and if you dry it further, it will result in shrinkage. So long you remove the capillary waters or cell cavity waters, there is no problem, but the bound water, the moment you start removing them, that can result in shrinkage, that results in shrinkage. And water up to which drying up to that water does not result in shrinkage, that water we call is fiber saturation point. Fiber saturation point, we call it fiber saturation point. So, fiber saturation point is what? It is the amount of water at which actually the cavity cells are empty, but the cell boundaries are cell boundaries have their bound water there. That is what we call as fiber saturation point. That is what we call as fiber saturation point, right. This is an important aspect. Now, if you look at this diagram, if you look at this diagram, you see, if I reduce my moisture content 40% here downwards, let us say, if we reduce our moisture content, right, and you can see approximate x axis is the dimensional change. So, this was my original dimension, let us say, and along the radial direction and also in the tangential direction. So, since I told you about the fact that wood is anisotropic, its properties could differ along the radial and the tangential direction, actually they differ, and because growth is along the radial direction, and in tangential direction if you go at certain level, the molecular structures are different that we have seen yesterday. So, if you look at radial direction, the moisture content or dimensional changes, as I change the moisture content from 40% to 30 to about 27 as I said, which is the fiber saturation point. So, as you reduce the water content, as you reduce down the water content, there is no dimensional change till fiber saturation point, because what is happening actually low bound, weakly bound, not strongly bound, that is water which are there, which are bound to the structure of the wood by weak bonds, very weak bond, capillary bonds are relatively weak. So long you empty them easily, the cavity becomes emptied. So, when cavity becomes emptied, there is no change in the overall structure, and therefore, up to this point either radial or tangential, there is no change in the dimension. But if you now start further drying, right, and reduce down the moisture content much lower, then you find that it shrinks, dimensional changes, approximate change in dimension, that means it will shrink. So, the shrinkages takes place, and of course, this shrinkage is measured with reference to 0 moisture content. So, shrinkage takes place as I go down, shrinkage takes place, and this results in defects. We will see these defects again in more details, because this can result in defect, and we will name these defects later on, each of them will name them. So, this can result in formation of certain defects in the timber as it shrinks. We will see this defect in more details. So, you can, but then you can't use wet timber, wet timber cannot be used, right, and you got to dry it from wet to fiber saturation by capillary movement simply, but beyond that you will actually require some heating, right. So, actually what is happening till the cell cavities are full, these are all capillary water. The further removal of water is nothing but physically bound or chemically bound, first physically bound hygroscopic water, and then this chemically bound with cellulose material or cellulose fiber, cellulose molecule, the water that is bound chemically with the cellulose molecule, that is what you will be removing. Now, this water is hygroscopic, right. So, if you want to remove them, you have to give more energy, that is number one. And wood in actual structure or in its use, it would be in conditions where you would be, the relative humidity would not be 100%, it will be much less. So, actually drying would take place in actual use. The moisture content, what is known as equilibrium moisture content with the atmosphere, depending upon the situation, whatever is the relative humidity and the condition of the atmosphere, wood will go on losing its moisture, and it attains what is called an equilibrium moisture content with the surrounding. That most of the material does. So, this equilibrium moisture content, the equilibrium moisture content, it should be such that moisture content of the environment and the wood should be of the similar nature, so that it does not lose too much of moisture while in use. And if it loses too much of moisture, then there could be shrinkages in use. So, that is why we would like to ensure that it does not lose much water. But below fiber saturation point, the moisture can be lost as vapor, and if there are vapor present in the atmosphere, it can condense into the wood again. So, moisture condition can go on changing depending upon the actual moisture content of the wood and the atmosphere, surrounding atmosphere, relative humidity of the surrounding atmosphere below the fiber saturation point. So, when you have low, let us say you have something like 20% moisture content in the wood, and atmosphere is such that it can absorb a lot of wood, the vapor pressure within the timber and outside is lower, then it would absorb some amount of the moisture vapor. Atmosphere will absorb some amount of moisture vapor, and on the other hand, if the atmosphere is dry, I mean saturated, and wood is relatively dry, there can be some amount of condensation within the wood. So, there could be transfer of moisture vapor from wood to the atmosphere and atmosphere to the wood if there is a differential exists, if sufficiently large differential exists, right. So, both this can take place, and therefore, we would like to maintain condition such that not much of moisture transfer takes place from wood to the atmosphere or atmosphere back to the wood, resulting in shrinkages, right. So, that we do through what is known as seasoning. We will look into seasoning a little bit later. Let us see what are the effect of moisture on strength. The effect of moisture on strength is something like this. You see, this is my fiber saturation point. Beyond this, as I go on increasing the moisture content, there is no change in the strength. But lower than fiber saturation point, points lower than fiber saturation point along here, because this diagram shows moisture content along this point. This is my fiber saturation point, this is my fiber saturation point, and as I go down along this direction, my strength reduces. Strength, it is reducing. Strength is, strength is increasing. A drier material we know is stronger. Strength is increasing, and from here strength reduces, and it is constant beyond fiber saturation point, right? Because it is all saturated. It is all saturated. No further moisture would affect anyway. But we know that when you have less moisture, there is a reduction in, increase in strength, and this happens in all materials in connection with the basic phenomena behind we have discussed in case of bricks as well, bricks and concrete as well. So, as moisture content reduces, the strength increases, and it can be sufficiently large. Of course, it can be sufficiently large in oven dried condition. Obviously, it will be it will give you high value of moisture, strength would be relatively high. I mentioned to you something called seasoning. Now, seasoning is to avoid shrinkage after fabrication of the timber, because timber, when you dry timber, after when you dry, it can shrink. So, if this shrinkage takes place after fabrication, after it is in use, then obviously it would, the functional performance of the timber, either as a structural member or as whatever way you are using it, that will be lost. So, therefore, we do not want any shrinkage after fabrication, and it must be in close to the right to the equilibrium moisture content with the environment. So, we dry it right in the beginning before putting it to use to such moisture content where it is likely to be in equilibrium with the environment, and that process we call as seasoning. Seasoning is basically controlled loss of moisture from green timber. Green timber, as it is taken away from the it is after felling of the tree as you get from the tree. So, this seasoning is basically loss of moisture, controlled loss of moisture. Natural seasoning is drying with circulation of air, and one must avoid differential drying. One must avoid differential drying, because if the top surface is drying at a faster rate and inside is drying at not drying at the same rate, what will happen? There will be shrinkages at the top and bottom would not shrink to that extent, it will resist that shrinkage and that will result in cracking or warping or some defects at the top surface. So, differential drying is not desirable. If the core and the surface must dry at the same rate, that is the idea, right. And one can have natural seasoning or one can have heating, because up to certain point you can do natural seasoning. What is done is, after sawing of the timber, air is circulated, they are stored and air is circulated through them, and if you circulate the air at the normal temperature up to certain point of time, up to certain level of moisture content, they will be actually dried, but below that moisture content you have to supply heat, right. So, you can say that this is up to this moisture content. You see, my fiber saturation point is here, fiber saturation point is here. So, till this point, beyond this point the shrinkages takes place. Above this point, of course, it has above this point is fiber saturation, roughly about near about fiber saturation point, right. So, from this shrinkages takes place. So, what we do is we actually dry up to this point, say about 18% moisture content or so. It is possible to dry with the air, right, air drying, and below that of course, you need heat. So, hot air can be supplied, hot dry air can be supplied, so that you can reduce down the moisture content, you can dry it off, but in a controlled manner. The rate has to be such that the rate of drying of the surface should be nearly same as the rate of drying of the core, or the amount of heat transfer from core to the surface or moisture transfer from core to the surface is same as the rate of moisture loss from the surface, right. Now, you can see that this is if you see this, first of all, let us see, this is where you are likely to use the timber in area very close to the heat source, let us say. Then the moisture content, equilibrium moisture content will be very low. Therefore, you should do the seasoning or drying up to this temperature. If it is kept again not close to the source, but a highly heated zone, then possibly this line 10% or so. Heated building could be about 12%, right. Normal building not much heated, about 14%. Garden furniture somewhere around 16% or so on, right. So, this similarly exterior joinery and so on, where you are expected to apply pressure, decay, this up to this is there will be no decay safety line, below this up to this is decay safety line, and above this there can be other kind of effects coming in. So, you can see along this in this diagram, you can see in this diagram that different condition warrants different moisture content to be there. For different environment, a different moisture content to be there, where you expect that there will be no shrinkage. Atmospheric moisture content is about 26% or so, you can leave it at 26%, but if it is likely to dry out at lower moisture content, then you cannot keep it here, because they will show excessive shrinkage at that point. And you can see this range of moisture contents attained through air drying of timbers. So, this is the range of moisture content which you will attain through air drying, and beyond this point of course, you need to have energy. So, seasoning is essentially done in order to attain, especially controlled drying, in order to attain a moisture content, equilibrium moisture content with the environment where actually the timber is likely to be put in use. So, that is what is seasoning, Now, improper seasoning can result in various kind of defect. For example, end splits, like this one, end splits as shown, surface cracks are forming, then this is wash boarding, something like this, right. Various kind of defects that can come. This is called cupping, and honeycombing, there are gaps here. Well, this can come from cupping, can result from seasoning defect. Then other defects are twisting, bowing, springing. All these defects are possible in timber after sawing and seasoning. Now, if you see the seasoning defect, drying, basically cupping is this one. We showed it earlier, we looked at, we had similar diagram earlier also. Cupping is rains on boards on drying. It would show you that if you just dry it, not proper seasoning, this is cupping, and this is diamonding. Actually, its original was this. After drying, shrinkage, it is diamond shaped. Then elliptical deformation, a circular one turned into an ellipse. Of course, here there are no deformation on radials on board, but this is cupping. This is again cupping. So, this kind of defects one can see in case of timber after seasoning. Now, what are the properties of the timber? They can be related to specific gravity. Now, one thing, first of all, we can see the values of this specific gravity, which are, this axis is specific gravity, and these values, as you can see, are order of about 0.1 to 1.1, which means that the density would be varying from about 100 kg per meter cube to 1100 kg per meter cube, which is fairly small compared to the other materials that we have looked into so far. Their density, specific gravities or densities were much higher. So, this is a relatively light material. This is a relatively light material, and its modulus of elasticity, you can see that in air dried and green condition, that is before drying, the modulus of elasticity falls into kind of a band, and you can therefore relate it to the specific gravity in this manner. It is simply a linear specific gravity, you can relate it in this manner, specific gravity to the power something, some sort of exponential form one can relate to, right, and this one air dried situation, which is higher, one can relate to this. So, modulus of elasticity could be related to this. Now, timber is a very resilient material, as you know, and its Chastain diagram, it's almost brittle, straight brittle, depending upon, of course, whether it is along the grain or perpendicular to the grain. If when it is actually pulled under tension or compression along the direction of the grain, if you try to pull it, of course, this will be a fiber breakage. If you try to compress it along the parallel to the grains, the grain failures do take place, but when you are trying to compress it perpendicular to the grain, actually it compresses and it does not break, it just simply compresses up to certain level. So, actually failures are defined accordingly depending upon the rate of deformation or total deformation, etc., wherever appropriately they are defined in terms of those wherever required. Now, in any case, it can absorb a lot of elastic energy, it is resilient, and therefore, where you have shock and impact, they were earlier used very much when timbers were available in plenty. Today, of course, timbers are not available as much, and we do not, its use is restricted from environmental point of view. However, it has got, it is a highly resilient material, it can withstand, absorb a lot of energy within elastic range, and it has got good elastic recovery. So, anyway, this is modulus of elasticity, this is modulus of elasticity. If we look at strength, strength can also be related to the specific gravity very easily, strength can also be related to specific gravity very easily. This axis is again specific gravity, this axis is specific gravity, and this axis is compressive strength, this axis is compressive strength, and you can see then these are also related to the specific gravity G. These are also can be related, this can also be related to specific gravity G, and as density increases or specific gravity increases, strength increases, this is well known to us. So, strength increases as specific gravity and increases, this is well known to us. So, this is what the properties of timbers are, Now, of course, there are gradation of timbers in terms of softwood and hardwood. Softwood are generally weaker ones, hardwood are the stronger ones, and structural gradation is available in the Indian Standard Code for various types of timbers to be used in structural situations. But more importantly, today in fact you do not use the timber as it is, you rather use it as kind of industrial product, because use of timber directly is not very efficient. As we could see, there are a lot of varieties of defects those are possible. There can be a lot of wastages, first of all the wastages in conversion itself, and then defects in terms of the inherent defect in the tree like knot, where actually grains are no longer parallel, but they form a kind of a knot as is called, and therefore, these are weak points in the timber. So, there are a lot of wastages and its properties differ from because its anisotropic properties differ, properties in the perpendicular and to the direction of the grain and perpendicular to it, they differ. So, what one can do, one can actually make use of make use of small timber pieces or process them at a small level and then join them, reconstruct them together to get more efficient system. For example, deficiencies in timber reduced by processing small units. So, you process small units and they can be by and large defect free, and then you can design them and then reconstruct the whole thing by some sort of bonding, because today you have a lot of bonding material available. So, you can reconstruct them using bonding. For example, you can bond the way you like. So, you can design this material. So, this timber boards are those kind of products which are actually produced by processing small units and reconstructing them by bonding. The boards will have much less variability, stronger as we desire, and will not shrink, because we are using pieces, very small pieces, or they are bonding them, gluing them, right. We will see some of them. What to use, like we know that plywoods, for example, plywoods, particle boards or cement bonded boards, and some, these are some examples. We will look into some of them, we will look into some of them at the moment, we will just look into some of them, right. In case of you can bond layers, to form a sandwich with strong leaves and soft cores. Now, if you remember, we talked about sandwich construction, something like this. You have a possibly a leaf, and you have possibly another leaf. You have a leaf, you have one leaf and another leaf, and in between you have some other core material. In between you have core material. Now, you remember when you are talking of polymers, we are talking of such sandwich material. Now, such sandwich material, when you apply transverse loading, say load along this direction, load along this direction, when you apply transverse loading, the bending stresses are maximum at this point. We know that bending stresses are maximum here and here, because the maximum compression will be here, maximum tension will be here. And the core is supposed to transfer is a shear connector, basically transfers the load from one leaf to the other through shear, because this will bend, right, and get a shape, its dimension will be shortened. If you see the next layer which is bonded to it, it will be shortened relatively less, and so on and so forth. And at the center, the neutral axis, we know that it does not actually, there is no change in the dimension, that is what we assume in linear elastic theory. And as we go below this, each layer will be actually longer than their original dimension. So, in the process, therefore, if there is bond, this is how it will get transferred. From the top layer would try to shorten the next layer, and next layer will try to shorten the next layer till the neutral axis, and below the neutral axis it will actually cause elongation of those layers. So, therefore, purpose of this core is to transfer, shear transfer, and we know the shear stress is maximum in case of bending shear is minimum here, and it increases in a parabolic manner, and maximum is here, shear stress is maximum. So, where bending stresses we know is something like this, bending stresses are something like this, maximum at the top compression and maximum tension at the bottom. So, this you know, therefore, and shear stresses are maximum here. The core should be withstanding maximum shear, and the leaf, outer leaf and the bottom leaf should be withstanding the tension and the compression. Now, this same idea can be used here also. So, we can make a kind of sandwich structure with strong leaves and soft cores. So, strong leaves can withstand the forces, bending forces, and core should transmit the shear, it should transfer shear transfer, and also might give other properties, improvement in kind of other properties. So, assembly of bonded with the direction of the grains in adjacent layer usually at right angles. So, this assembly of layers are bonded with the direction of the grains in adjacent layer usually at right angles. Now, why is this? Basically, if you have if it in one directional, the forces you will get, I mean the properties you will get is directional. It is making, if they are perpendicular to each other, if the directions of the grain are perpendicular to each other, then the strength will be same in both the directions. So, both in horizontal x and y direction. In z direction, if you apply the load, let us say a plywood board, something like this, which you shall see later on, it has got a sandwich construction, a top layer, a bottom layer, and the core. In the core, you have actually sort of pieces or small pieces, with such that their grains are perpendicular, grains in adjacent layers are perpendicular, such that the strength will not be directional, it will be both directional. So, outer inner plies are symmetrical to the central core. So, outer and inner plies are symmetrical to the central core, right, outer and inner plies symmetrical to the central core, and that is how they can withstand a lot of load. There are different names of the similar kind of materials. The block boards have core made up of strips of wood. You can make them up of strips of wood less than 25 millimeter thick, and lamin board have less than 7 millimeter thick woods, as we shall see. These are bonded with the glues. Now, you have polymeric glues available. For example, glues we have discussed about the adhesives like urea formaldehyde or phenol formaldehyde or melamine urea formaldehyde glues. So, these glues are used to bond this, and once you bond them, you get right kind of property. Durability, of course, of the wood will depend upon the wood species itself. Durability will depend upon the wood species itself, right. It will depend upon the wood species itself. For example, this you can see is the plywood. Now, you can see this is the soft, this you can use. So, you can make use of soft wood and soft and hard kind of, and this ply again could be bonded, bonded with glue, could be bonded with glue fiber boards basically. Now, here you can see this is the grain direction, this is the grain direction. So, they are perpendicular to each other. For example, if the grain direction was all in the same direction, so it would have strength only, if in this direction the strength would have been, I mean all in the same direction, let us say all in the same direction, then strength should have been higher along this direction, along the direction of the grains, and low along the perpendicular to it. But making some grains along this direction and other grains along this direction, its actually properties along this x and y directions are made equally good. And you can see this is the softwood strip, this is another softwood strip, another softwood strip, and so on. And this soft wood, since it is not expected to take too much of the load, because it would, the transverse load, when I apply load like this, the load would be taken by, the bending stresses would be taken by this outer leaf and the bottom outer leaf, and this would only transfer, will be ensuring shear transfer and take shear transfer is ensured by this. So, therefore, these leaves are meant for taking transverse load, and these boards, so we can use strong this board, but softwood can be used here. Similarly, the lamine board, as I said, this soft strips, this is 7 to 25 millimeter. One of them we said block board. So, this is a block board, and lamine board the one I said. So, there is strips, simple strips along this direction, strips of simple softwood strips along this direction, and you have a hardwood veneer, right. So, it is again kind of a board, basically a strong board. So, this is this forms the leaf, the bottom one forms the leaf, and all these are joined by glues. These ones are joined by glues, and this one is also joined by glues, and therefore, it gives you the requisite kind of strength that you desire. Then there are particle boards. So, one thing is you use, in the previous case plywoods, basically you are using small pieces of wood. You are using small pieces of wood, and you can see that this otherwise may not have been used. For example, the soft wood pieces which you have used, they are not very strong, but you have used them efficiently by re-engineering the whole thing, or rather kind of reconstructing the whole thing, and it is a definitely more efficient use than using direct using the direct timber just as it is, or after conversion, straight away after conversion. So, another kind of very efficient use is particle board. Now, these particle boards are manufactured from particles of wood, flakes. So, if when you actually polish the wood, you get shavings, wood shavings, right, with a file. You polish the wood with files, then you will get shavings, you will get flakes. The chips would be there when you have cut it into let us say when you have actually cut it into some sizes. Then sawdust would be available after sawing, and this sawdust would be available after sawing. Wafers are available at certain places. Strands can be made available while processing the wood. So, all this comes from processing the woods, and normally they would have gone as waste. Now, so these materials can be used together with some sort of adhesives, glues, and use heat and pressure to form boards, and they can be used efficiently for various purposes. Now, not only this, you can use other lignocelluloses or lignocellulosic products, under heat and pressure with adhesive to get this particle boards. You can make them layered boards, you can make layered boards, right, you can make layer boards. In fact, considering that plywood earlier, one can think in terms of layers even there, like something like this is one layer, right, this is one layer of the material, one layer, first layer, there the orientation of the fiber will be like this. A second layer could be orientation of the fiber could be along this direction. So, those are, even in plywoods there can be several layers overall, or boards, various kind of boards where there can be more layers. Now, here these are boards can be assembled in 3 or 5 layered boards. They can be assembled in 3 or 5 layers, and you can have also other kind of boards such as cement borded boards with usually such kind of materials as the wood shavings, chips, sawdust, wafers, etc., strands, and other kind of material. Together with this you can bond with cements. So, it is something similar what we have done in case of, let us say this here in case of many of them we use polymeric bonding agent, and some other cases you can use cement bonding agent, right, and you can foam them. Now, foaming means what? Basically you can make them lightweight, so that you can it can be used for various kind of insulation purposes. So, can be used for various insulation purposes, right. Fiber boards are they have thickness of about 1.5 millimeter or greater, and they are manufactured from these fibers. So, earlier what we have seen plywoods actually uses small pieces of the wood themselves, they are glued together. Plywood uses pieces of the wood and they are glued together, right. And in case of particle board, the wood wastes of various forms we are gluing them together. So, first one was the wood itself is being glued together, pieces of woods. Second one is where we are actually the waste, finer ones, finer wastes, we are gluing them together. And now we are trying to look at the fiber themselves. So, supposing the cellulosic fiber, we take them, right, or any other form of lignocellulosic fiber, we take them, and then under heat and pressure we join them, either using a synthetic binder like urea formaldehyde binder, some sort of glue. So, you bind them together and then compress them, right, under pressure and heat them up, or use this material fiber themselves, so that they bond themselves, right, they themselves bond by felting, so you they become form a felt when you compress them under pressure and heat them up. So, by felting they bond themselves, let us say, it is one thing, and second case could be used a synthetic fiber. So, what you get it is a fiber board. The thicknesses of are small, 1.5 millimeter or greater, and these fibers again can be used as leaves, outer leaves, or leaves for other kind of sandwich construction. Right. Then there are compressed straw boards. Straw can be used as a material, and compressed straw boards, you can make slabs, actually straw building slabs, right. Now, here you use straw, you compress it by heat and pressures, actually you join them, you compress it by heat and pressure and join them, right, by putting papers, bonding papers with it, and you form a kind of slab. So, papers and straw compressed together with papers at the top, bonded together, and this kind of thing you can form into slabs. Now, this will be very lightweight, and as you know, lightweight materials forms good thermal insulation, lightweight, lot of porosity. Straws are very porous, they are very porous, and when you actually put the paper as the restraining and bonding material, you bond with the paper. So, this forms a very lightweight material, and its thermal conductivity should be less than 0.1 watt per meter degree centigrade, and you can have thickness of the 50 millimeter or so. Now, this would form good insulation material. This can form good insulation material, this can form good insulation material, right. So, particle boards and then straw building slabs are something like this. I said that cement can be used for bonding purposes, like particle boards can be manufactured with cement. So, you have same cement, in sort of cement mortar preparation, we essentially use sand. Now, instead of sand, supposing I am using wood shavings, wood sawdust and all that, therefore, I can get I can make it something of the kind of a board or a slab which will be fairly lightweight, and can be used as good insulation. Now, wool cement slabs are made from long wood shavings. So, you take wood shavings which would come from processing of the wood, and then actually they are embedded in cement or coated with cement, as we are calling, and then you compress them and they can be used as insulation. Now, wood itself, you see insulation essentially have very low thermal conductivity, and which is a function of the porosity, in other words inversely proportional to the density. So, should have in normal temperature we are talking of the thermal properties, or even insulation would like acoustic insulation, or such boards can be used as absorbers, acoustics purposes of spaces, they can be used as absorbers, because in the pores, when you have in the sound absorption, you need porous material. One of the technique to increase absorption is to have porosity, pores into the surfaces, right. So, when you have pores in the surfaces, what happens? The longitudinal sound wave actually would impinge onto this, and due to friction with the surfaces, certain amount of energy is converted into heat. So, there is an absorption. Porous absorbers are there, very common, and boards such as wood cement slab, or the straw board that I was talking about just now, they can be used as good absorbers for sound as well, because there will be a lot of losses, and you need absorption, sound absorption, when you want to control the sound generated within the room. For example, a sound is generated within the room and you want to control control the acoustics of the room itself, and the noise is also, or the sound is generated within the room itself. You would need lot of absorbers at certain places, because many times you may not like the reflected sound to come back. Most situations like in auditorium, in certain locations you don't want sound to reflect back into the auditorium, especially from its rear portion, which causes some sort of defects in the acoustic defects. So, absorbers are used, and these materials can serve as both thermal and good acoustic insulation. So, wood wool cement slabs are made of long wood shavings coated with cement and compressed under pressure, and they can be used as insulation. So, these materials can be, they can, all these materials, therefore, the straw slab I talked of, and similar other kind of particle boards which are generally lightweight in nature and have lot of pores in the system, foamed cement particle board. They can be used at good thermal insulation in or say in partition walls. They can be sandwiched between harder leaves in order to make good thermal insulation. So, construction can use them. Then this is glued laminated timber, consists of timber lamination bonded with adhesives, so that grains are all parallel or longitudinal direction. So, you can now choose the timber pieces and then glue them together in such a manner that in a given direction all grains are parallel to a given direction, which what you do then in essence, you are making it strong in one given direction, and so properties is utilized in a given direction. So, this is called glued laminated timber, in short form it is called GULAM, and consists of timber lamination bonded with adhesives, so that grains are all parallel to longitudinal direction, right. So, this is another product. Now, with this kind of products now available, there are various kind of flush doors available, right. And just as an example, there are similar sort of products which are used in buildings and constructions from timber. Of course, use of timber as such, although has become less popular now because of its availability, but it has been extensively used in areas where timbers are grown as as for example, in trusses, in truss roofs. So, truss roofs, timber roofs are very common in many places. Timber roofing system, I mean timber frame or timber truss, they have been used for building construction for many years earlier, but now their usage has reduced because of the availability of the timber. Similarly, the columns particularly in northeastern part of India, or let us say Himalayan areas, people would have used timber very much. Even floors of timber, floors have been used in cold areas of Meghalayas, for example. Two advantages, because they are lightweight, can take a lot of, they are resilient, can absorb a lot of energy. So, therefore, from traditional point of view, they have been used extensively from consideration of those areas happens to be also earthquake prone. So, timber structures were very popular in those areas earlier, but now availability of this timber directly has reduced significantly. But industrial uses from this products, because you use less amount of timber would be used less, so we got to use it more efficiently. In case of doors and similar structures, plywoods and other kind of boards that we talked about, they are being used extensively, and they are still quite popular. So, some of those flush doors which are available, they look like this. For example, this has got hollow and cellular cores. This has got hollow and cellular cores. This is small buttons here, right? And this is core is actually, this is the voids should be there in between. So, there will be voids here, buttons, and there will be buttons, and there will be in between voids. And you have one leaf, maybe there is another layer inside, and here in this case you say you have got again the rails, intermediate rails and battens. This is the rail and this is the batten, and in between you have got voids, actually in between you have got voids. So, it is a hollow and cellular core, definitely would be lightweight, mainly meant for doors, definitely would be lightweight, and you know, it would be definitely lightweight and also sufficiently strong, because you have got the leaves here. Now, the door essentially is likely to you know encounter loads, transverse loads, and therefore, this leaves, which not only gives you aesthetic look, but also provides strength, required strength in the given under given mode of action of the load, right. Inside you do not need much strength, and therefore, you can make it hollow, and therefore, this is one type of those. So, hollow and cellular core type of door is one of the types. If you look at this one, block board and particle board, in this case you have, you know, again this, first of all, the outer face, the veneer, outer face veneer, then you have got cross band, right, internal another layer, then you have got block board core. So, this is a block board, actually block board form core here, and in this case you have got a particle board or, you know, macro defect free sort of cores, and this forms a door structure. So, it is actually a composite with core being of some kind of board, particle board, or some sort of one type of formation, the leaf being, layers of leaf being different, and you can have actually combinations and design them in I mean according to your requirement. So, this sort of industrial timber product, they have become very popular, because they are efficient, more efficient in use, you know, their user efficiency in use is much higher than direct use of timber, right. Now, certain other aspects of timber that usage we have covered, but certain aspects, other aspects of timber, for example, their durability and deterioration, this we have not covered. One of the major cause of deterioration, of course, is a fungal attack, attack by fungus, because fungus goes, this is a material where you know, those insects can grow, the fungus can grow, and therefore, it deterioration processes, you know, fungus, effect of fungus is one of the important issue related to decay and deterioration of timber. Now, that is why it is you cover them up with paints and varnishes, and preservation, as we call it, and that is what we do. But however, you know, I would like to add preservation and details of this preservation and deterioration process in timber. Of course, we can't cover them because the time that is available to us. Now, use of timber has become much limited than you know, much less than what it used to be earlier days, from the simple concern of environmental concern. So much so that certain organizations do not recommend use of timber directly. So, only processed timber you can use, and efficient use of timber is very much necessary, because you know, deforestation is a major environmental concern, and therefore, timber, although it is a natural product, was used was available very easily. Now, it is not as popular as it used to be, and materials like other materials of the kind that is available to us, many of this partially man-made or fully man-made material, that is become much popular. So, I think this is our discussion on timber. So, we can summarize our discussion from the beginning. What we have discussed, we have looked into, we have not gone in of course, we couldn't discuss in great detail about timbers, whatever was possible. What we did is, first we discussed about the growth of the tree, and you know, from where actually the timber comes from. Then we looked into some of those processing, namely conversion. Then also we have looked into its chemical nature of the timber. There are other issues related to molecular structure of the timber, not molecular structure, but general structure of the timber, which really we did not look into. And then we looked into importance of the moisture content, because this is one major issue related to timber. The moisture content is issue of moisture content, that is very important. Then we looked into seasoning, how we control the moisture, and then some of the uses, sort of industrial products, timber products. The direct timber products, of course, we did not look into. So, I think that should summarize our discussion. We have looked into structure and properties, and then we looked into mainly into industrial product, right. So, with that our discussion on timber and module 13 concludes. In the last module, we will discuss about different types of, something about roofs and floors. Thank you very much.